QuadQuiz!
Brought to you by Math with Sir Lester. There are 3 questions for this video, and you are to answer them in 15 seconds each. Are you ready? In 3, 2, 1. Let's have this given quadratic equation and look at our a coefficient. It's no longer 1. Is this trinomial factorable? Yes or no? The answer is yes. Now, what are the factors of this given trinomial? The factors are 2x minus 3 and x plus 2. With that, what are now its factors? The factors are 3 halves and negative 2. Did you get 3 over 3? If not, please continue viewing this video. Whenever our quadratic equation has a coefficient not equal to 1, in this case it's 2, we are going to expect where we have a root that is fractional in form. So we are going to use the correct processes here in order for us to take the roots of this quadratic equation. But first, again, we know that a is no longer 1, it's more specifically 2, b is 1, and c is negative 6. Why are these coefficients important? First, of course, we have a quadratic formula that will allow us to solve the roots of any quadratic equation using these coefficients. But we are not going to use that in this video. We're going to use the other methods. The previous methods presented was extracting square roots. That is when b is not around. But since b is 1, we cannot use that. And we also have a factoring, specifically the common monomial factoring, that is applicable when c is 0. But since c here is negative 6, we cannot use the common monomial factoring. But we can still use a portion or a sample of factoring if this trinomial is factorable. And if it's not, we are going to use the completing the square method. We can identify that by AC. AC means we multiply the a and c coefficients of our expression. You have 2 times negative 6. Our AC is actually negative 12. Then we are going to look for factors of negative 12. I believe there are more than 4 pairs here. Let us try to determine them. Of course, we could have 1 and negative 12. We could also use negative 1 and positive 12. When we multiply these 2 pairs by its partner, you will get negative 12. Next, we'll have 2 and negative 6. And we could also have negative 2 and positive 6. And we could also have 3 and negative 4. And also negative 3 and positive 4. I believe these are the 6 pairs of integral numbers or factors of negative 12. The next here is we need to examine if there is a pair here that when they are added, you add them up. If there is a pair that when added will result to our b coefficient of 1, then we are 100% sure that this quadratic trinomial is factorable. But if in this case among the 6 we cannot look for any, then we proceed with the completing the square method. When we look at all of the 6, we can see this portion here. Negative 3 times 4 is negative 12. And negative 3 plus 4 is positive 1. And since we have located this, we are sure that we can use here factoring. If ever, again, we cannot look for a pair that will result to B when added and AC when multiplied, then we proceed with the computing the square method. So there might be examples later. So in factoring here, since it's a trinomial, quadratic trinomial, we expect two binomial expressions. Last time, we used x and x here. Because it was x and times x, you will get x squared. But since we have here 2x squared, we need to expect that one of which is 2x and the other is x. So that 2x times x, you will get 2x squared. And we can now place both of these coefficients here. But if we're going to place them automatically, let's say here and let's say here, look at the result of the last term on the FOIL method. Negative 3 times 4. That's not negative 6, it's negative 12 actually. So there is still something I need to do. And this is unique if our A coefficient is no longer equal to 1. My suggestion here is for us to, for us to make use of this, okay, here. We are going to, let me redo everything. Okay, so it won't be removed. So let me take this out here as well, and then let's return the color here. Okay, so instead of x times x, of course it's incorrect, and of course except for x times 2x, I would like to advise you to place two 2x's. If you're going to multiply 2x and 2x, of course it will not return to 2x squared, but more importantly it's 4x squared. But there is something that we need to do later. This is just to make sure that we could easily and more comfortably place the coefficients of the pair that we have decided earlier. Of course, again, 2x times 2x, that's 4x squared. Even the last is negative 12, not negative 6. But there's something that we could do here. Look at this pair. Both coefficients are divisible by 2. This is made possible because when you really push for these two factors to be multiplied, you will get a version of your equation with the multiple of 2. So just by this time, we could automatically divide it by 2. This first binomial, of course, the greatest common factor of 2 and 3 is 1, so don't need to divide by 1. So let's have it here like this. 2x divided by 2 is simply x, and 4 plus 2 is just 4 divided by 2 rather is 2. Now, this is not the better factor. If we're going to check, okay, 2x times x, 2x squared. That's negative 3x. That's 4x. So negative 3x plus 4x, positive x, you achieve b. And of course, for your last, negative 3 times 2 is negative 6. Okay? So this is not the correct factors, and let's equate it to 0 because our goal is not just factors, but our goal are the roots. So according to our zero factor property or the zero product property, this situation is only possible when one or both of them are equal to 0. And with that, our first root will have here 3, positive 3. X is equal to 3 halves, positive 3 halves. That's your first root. And your second root is just negative 2. So these are the two roots of this given quadratic trinomial. It's a little bit longer because we have a coefficient no longer 1. And what is unique here is again the trinomial is factorable, and we use the AC way for that to determine that truthfulness, and we use here the factoring in order for us to get these two roots. This is the discussion for this QuadQuiz. Subscribe now.